Okay. Yeah, thanks everybody. So Coralie mentioned a lot about our optical navigation experience at Pluto and capabilities that we've developed since then for the other missions. She also mentioned that kinetics and New Horizons are closely integrated in their formulation and their start. And so it was really interesting learning about the history of New Horizons this week from my perspective, because I joined in 2013. So I wasn't there for all the past history, but it's integrated with our company and our recent collaborations and success. So it's interesting to hear the history there. So thank you all for that. Okay, so what is navigation? Corley talked about OpNav, but that's just one component of the larger navigation team. And so really, obviously from the high level perspective, the responsibilities are to determine where the spacecraft was in the past, where it is now, and where it will be in the future, with some sort of level of uncertainty prediction. And then also determine what maneuvers are needed to get the spacecraft to the target. So we're all familiar with the New Horizons trajectory, flying by Jupiter in 2007 and then going out to Pluto in 2015. But some of you might not be as familiar with this graphic on the right, which is what we call the B plane. And so this is really how we define the navigation requirements for a flyby such as New Horizons at Pluto and then New Horizons to Arakoth as well. But basically what I'm showing here, the box here is the requirements, and then the circles are the different solutions or navigation solutions on different days as we get more and more data in the last week before the closest approach at Pluto. The left is what's called the B plane, which is sort of your, I have a graphic to show this later, but it's basically the plane that you intercept as you fly by Pluto, essentially. And then on the right, importantly, is your time of flight or time of periapsis, which defines the time at which you fly by the object. And so those define our requirements in the space that we're trying to navigate to for a flyby such as New Horizons. So Glenn kind of showed a little bit about this earlier, but the way that our navigation ground system works is we get tracking data, which is radio data and the optical navigation images from the spacecraft through the DSN at JPL. We process those and we basically have this network with APO where we send them trajectories, they upload them to the spacecraft, maneuvers, uploaded to the spacecraft, executed, et cetera. So we all work very closely together. And as Corley mentioned, for the Pluto system and Pluto flyby, it was also very important to collaborate with the science team because we needed to model a lot of the albedo variations and parameters of the Pluto and Karen albedo to do the optical navigation successfully. So the way that navigation works is basically, Corley talked about this first block, which is optical navigation, which is the image processing. And that goes into a filter, which we call OD or orbit determination. And so that combines the radiometric data, which I'll talk about in a second, with the optical navigation images. That produces a solution of the trajectory relative to, in this case, Pluto and Charon and the moons, which we then propagate forward with some level of uncertainty. So if you're familiar with astrometry, this is a very basic principle, but basically the more data you have, the further in time, the smaller your uncertainties, and the less data you have further out in time with longer propagation, or long mapping is what we call it, the higher your uncertainties are going to be. So as we gather more and more data, as we approach Pluto in this case, our uncertainties get smaller every day. This is a graphic of that B plane, which shows it's basically defined by your incoming velocity vector, which is called the hyperbolic velocity here. And then that's the B plane, the plane here that it pierces, and then the time of flight is the time at which it pierces that. Okay, so I'm going to quickly browse through this because this just shows from a very high level how the navigation works and how we incorporate the optical navigation measurements, which was one of the key lessons and unique challenges for New Horizons as opposed to other planetary, even outer solar system missions to larger planets. So we start with, the Earth with respect to the solar system barycenter, and then you collect range measurements using the signals from the Deep Space Network to give you the range to the spacecraft. You can also do the same thing with the frequency shifts, which gives you the velocity along the line of sight using Doppler measurements. So that gives you the position velocity along the line of sight of the spacecraft, but we still don't know the cross-track measurement at this point. So what we do there is you use delta differential one-way range, where you use two different stations at the DSN, and you basically they calibrate the baseline with the quasar, and then you move to take a measurement of the signal at the spacecraft, and that delta angle is the what's called the delta door measurement. And so that is what gives you that cross-track information, which will give you the spacecraft position and velocity over time with respect to the solar system barycenter, but we still don't know where Pluto is. And that's because, as Corley mentioned, it had only been observed for 85 years, so the orbital period, or the uncertainty in the period rather, was still relatively unknown. And so because of that, and because of the fact that Pluto was not massive enough to show a gravity signal in the radio measurements as we approached Pluto, that requires the use of optical navigation to reduce those uncertainties. In particular, as Corley mentioned, the time of flight uncertainty because of that radial error in Pluto's ephemeris. And so that's where Corley mentioned how we do OpNav, which gives us that information there. And then to give a little bit more details about what Corley was mentioning with the moons, interestingly, if you think about what we're taking observations of as you're approaching a system like the Pluto system, you got Pluto, which is the most massive near the barycenter, which is just outside of its body there. And Charon, those are orbiting the barycenter out here, or in here. But way out here, you have Nix and Hydra orbiting at a longer baseline. And so what that information tells us as we approach the system is actually, it gives you the first sign of that parallax difference, or that information into the time of flight measurement as you approach. And so what's shown on this bottom right here is a plot of the, the position differences between the Pluto barycenter. So that's like our estimate of the barycenter of their system with respect to the solar system barycenter over time. And you can see this big jump right at around July 11th, which, if you recall, is only 3 days before the flyby. And that's really the point where we get this parallax information from Nix and Hydra specifically. And so it wasn't until the very end of the flyby, and we knew this, going into the approach, that we would get this information. That's the whole reason why we had last minute knowledge updates planned for the encounter. Another lesson learned that we worked on, or that really came up during the flyby, and Alan was very well aware of this because he was the one making most of these decisions, was that you had to approach, or you had to trade each maneuver decision between the fuel cost, which goes up as you get closer to the system, against the uncertainties in your navigation solution. So this is a good example here, where the big blue air is our air from OD 99. We acquire more data, those airs go down, but by acquiring more data, you also have a higher fuel cost by waiting. So trading those was, a challenging thing for something like this, where you're on the border of the requirements. But nonetheless, in this example, it was decided to do a maneuver after this solution, since we were out of the requirements and the uncertainties were low enough at that point, which is what's shown here. So here is our history of the TCMs, basically since a year before the flyby. So this is starting on July 7th. We did a maneuver TCM 15, which moved our beat plane over here. The requirements are tiny in here on this scale. Here's Pluto to scale. And then on the right again is the time of flight. So you have very large uncertainties. We corrected that a year out, did another maneuver on February 24th of 2015, which took our solution from here into a closer proximity to the beat plane. And that's this jump here. And then the very last maneuver, which is the one that I was just mentioning, was taking the solution from the bottom of these requirements closer to the aim point, which is in the middle there, which also moved our time of flight down in this direction. And at the very end of the flyby, that is where we pierced the B plane. And as Corley had mentioned, we did not perform a knowledge update in this case because we were already within both the control and the knowledge requirements. So those were sort of the three main lessons learned from a high-level navigation perspective. I also now want to kind of talk about what recent innovations that New Horizons and Pluto taught us. And one that I think is really interesting is there was a rehearsal in the summer of 2013 where the operations team put the spacecraft through a variety of activities to simulate exactly or nearly exactly what would occur during the flyby in 2015. So what that did for us from the navigation perspective is allowed us to look at the small forces or the delta V's that were acting on the spacecraft as it would slew to different attitudes and take observations of the Pluto system. All of this was simulated, but it allowed us to get a really good model for modeling those small delta V's, which allows us to do a better prediction of where the spacecraft will be in the future. So this is actually showing a much larger scale of that model, which is the blue curve here. The rehearsal gave us a lot of information into this very last piece here, the final few days of the approach. But you could see the actual reconstructed delta V, so that's what we saw in flight, what we estimated using the navigation filter, matched very closely with the model. And so we've used that for a lot of other missions since New Horizons, and most importantly was the Aerocoat flyby, which we actually needed to estimate and predict the small forces to an even higher level than we did at Pluto in order to specifically hit the B-plane corridor in such a tight window, and allowing the highest resolution image of Aerocoat here. Corley mentioned Lucy, but I will talk about some of the future work that we could still do with the Pluto data. We saw Paul Shank's work and others on the shape model for Pluto and Sharon. And so that's something that from the navigation team we could use to ingest into our process, like we did at OSIRIS-REx at Bennu and like we're planning to do at Apophis. And basically use that to improve our navigation solutions. So instead of doing the center finding that we have done with Pluto and Sharon and Nix and Hydra, we can actually use landmark navigation. So actually navigating and finding measurements with respect to the landmarks for the entire body of Pluto and Sharon. And that could help improve our navigation solutions going forward in the future. So there's always some future work to go. But I believe that is it. So I will take questions now.
Very interesting. Just a quick question. You had a slide that talked about, it called out unanticipated forces.
Yeah.
On New Horizons as it was making its long journey, and how that plays into your uncertainties that you have to correct for. What are some of those unanticipated forces?
Yeah, that's a great question. They're called gas leaks in our model. Now, for something like New Horizons, it's unlikely to be something like that. That's the historical term for it, gas leaks. Because at the time, in the early days, there were actually gas leaks going on more frequently. So for New Horizons, it's something like the RTG acceleration. So we actually see an acceleration from the RTG, the thermal radiation. That's a good example that we have to predict and estimate. But most importantly, the trends I'm showing here are residual delta V from the attitude control thruster. So like we were saying, there wasn't reaction wheels on the spacecraft, so the attitude is controlled by the thrusters. And because even though they're designed to be balanced perfectly, it's never perfectly balanced. So that's that's the highest level of delta V. Yeah.
Thank you.
Okay.
Online from John Cooper. With the remaining propellant, what angle off the present trajectory would be possible for a newly discovered object?
I would have to look at that one. Yeah.
Much smaller than a tenth.
Yeah. It's very small. Yeah.
And we're out of time. So
Thanks.
I don't have the exact number, but it's less than a tenth of a degree. 0.1 degrees, less than that.